All right, welcome back to this YouTube channel. So today we'll solve a problem on the wave function of the hydrogen atom. So we have a problem here, and we are asked to evaluate for the hydrogen atom. So we have to evaluate the wave function and the expectational value of the position R. So we are given the quantum numbers n equals 3, n equals L equals 1, and m equals 1. So first thing first, we know that our wave function for the hydrogen atom in 3 dimensions is given by this. So arrow subscript n of L is R. So this is our radial component, and this is our angular dependence. So if we write out our wave function for the hydrogen atom after solving for this, we are going to have this expression as a wave function for our hydrogen atom, where this part from here to this point is our radial component, Rn of L, which has been normalized, by the way. So we also have our angular part to be given by this expression as well. So we are just going to substitute for n, L, and m, and we are going to have this expression after substituting for n, L, and m. So if we compress this, we are going to have this expression for the wave function with quantum number 3, 1, and 1. Now we are going to expand this part, and we're also going to expand this hypergeometric function here. So if we do this expansion, we're going to have this as angular part for m equals 1 and L equals 1, and we are going to substitute it back to have this. So our hypergeometric function is given by this. This is the expansion of our hypergeometric function. So if we do the same thing here on this expression, we are going to finally arrive at this. So our rho in this case, our rho is equal to r all over 2 a naught. So not 2, please. It's n a naught n. So that is our rho in this case. So if we substitute it, we are going to have that expression there. And finally, this is our wave function for this state. So quantum number n equals 3, L equals 1, and m equals 1. So this solves our problem for Roman figure 1. So if we move forward to Roman figure 2, this is going to be the expectational value. Of course, it's in spherical coordinates. So we are going to replace this by this expression here. Don't forget, this is a complex conjugate of the wave function here. So finding the expectational value, to have this expression, substitute for a complex conjugate. So mind you, the difference is coming from here because this is where the complex term is. So we'll have negative on this one and we'll have positive on this one. So if we compress those two together, we're going to have this expression, which we can split out or spread out. We can take the radial component together, then we can take the angular component together, which is spanning from 0 to pi, and we can also take the phi component together. So this is the phi component, this is theta component, and this is our radius component. So we are going to have this expression after taking everything together. So this has been absorbed, this expression here has been absorbed into 8 pi over 3. Solve that by mathematics. So this is our final value we want to evaluate. So evaluating this gives us, we can just let gamma to be 3 over 2 over 3 a naught. So if we let gamma to be that, it means that we can have this power to be cleaned up to give us negative gamma times r, because we have taken them 2 over 3 a naught to be gamma. So we can evaluate these integrals. That is our aim. Our aim is now to evaluate these integrals, which by evaluation we can apply this this integration here. This integration here will be used to evaluate those integrals, and we're finally going to have this expression. So finally, our expectational value is 25 over 2 times a naught, which is the ball radius. See you next class, on the next one. Thank you.